Hello and welcome to day 14 of my Advent of Code series for 2020. If you've missed any of the previous episodes and you want to go ahead and get caught up, check out the playlist linked right up there, and be sure to get subscribed to me and turn on post notifications so you don't miss any of my future videos. So today we have day 14 docking data. So here we need to get our ferry's computer system to be able to interface with the docking system at the pier, and what we need to, or at the port. And so what we need to do for that is we need to pretty much emulate how some chip works in software by using this list of instructions to yield what the memory will look like at the end. So the way that this breaks down is we're given a mask and then we're given a bunch of memory address assignments. So how the mask works is if you have an X in its location, then it can take on whatever values passed into it. If it has a 1, then it puts a 1 there, and if it has a 0, it puts a 0 there. So what we have to do is for each memory address assignment, we have to take the integer here. Very annoying that they used things that could also be binary numbers here instead of using things that are definitely base 10 integers. We have to go ahead and convert these to a binary version of the string, apply this mask to them, and then assign this memory address to that value. So then once we're done with all of that, what we need to do is just return the sum of all of the values that are still in memory. You'll see sometimes things do get overwritten, so yeah, that's pretty much it. So we're going to go ahead and jump into my code right now. I recommend that you give this a try first because this one is definitely attainable. And let's take a look at my solution. So the first thing I do is when I read in these instructions, I go ahead and split every single line on that equal sign, because if you look at how the input works, it's sort of the instruction and then the actual value. So it's just easier to work with like that. So then for part 1, what I'm doing is I'm creating a dictionary called values. This is where all of our our mappings of memory addresses to values will live. I'm initializing my mask as just being essentially a mask that just spits back whatever it gets in. The reason I'm doing this is mainly just that my text editor stopped yelling at me about it possibly being uninitialized. This value is never actually going to be used. So then what I do is I loop through all of our instructions. If the instruction is mask, then I assign the value into our mask right here. Otherwise, that means we have a memory assignment. So what I do is I first get a list version of the mask, and this is going to be where I am actually passing in our values and replacing everything. Then I get our index. So our index is going to be this right here. So I do that by just chopping off the first 4 characters, which is always going to be mem open bracket, and chopping off the last character, which is always going to be closed bracket, to get our actual thing. So then we'll break down how I'm getting the value here. So what I'm doing is I'm getting an integer version of the value that's on the other side of the string. Then I'm converting that into a binary representation of it, which you'll see right here how this works. Then I'm converting that back into a string instead of being a binary thing. And then I'm cutting off the first 2 characters, this 0b, so that I just have the binary version of it. So then what I'm doing here is essentially just adding leading zeros to make it the same length as cur. So this is technically always going to be 36. But it's just, I thought it would be a bit more semantic to just say length of cur here instead of just having a random magic number. So what I'm doing is I'm subtracting the length of our value from the length of cur. That's going to give us how many zeros we need to put before val for it to be the same length as cur, and I'm just adding that many zeros onto the start of the string. So then what I'm doing is I am looping through length of cur, which is now also the same as length of val, and if cur's thing at that index is indeed an x, then I go ahead and replace it with val at that index. Otherwise, it's going to be a 1 or a 0, and I want to keep that in place. So then what I'm going ahead and doing there is I am saying that value subindex, remember this is where we're actually holding our memory mappings, is going to be the int version of the string of whatever is in our current list at the end of all of this in base 2, because this is going to give us a string that represents a binary number, so we need to convert it back into an actual number of base 2, and that will give us a base 10 number in our values mapping. So then once we're done with all of that, I just return the sum of all of the values inside of our vals dictionary. So that's it for part 1, and with that we can jump into part 2. So for part 2, it's not working, and we realize it must be because we need a version 2 decoder chip and not a version 1. So version 2, the difference is it doesn't modify the value, it actually modifies the memory addresses. So that and how the bit mask works is a bit different too. So if the bit is 0, then we do not change whatever's in the value. We just take in whatever is in our actual memory address that we're given. If it's a 1, then we go ahead and replace it with a 1. And if it's an x, then it is floating, which means it can be either a 0 or a 1. So it ends up modifying all of the memory addresses that fit the pattern of zeros and ones that are set, and then either a 0 or a 1 in the x right there. So it works through an example here. You can go ahead and take a look at that if you haven't already. I recommend you go ahead and give this problem a try, and then we will jump into how I did it. So for part 2, what I did here is pretty much, it's similar in structure to what we did in the first part, but let's go ahead and run through it. So I still have that vals dictionary, which is just going to hold all of our mappings. I initialize our mask with the zeros this time. Again, this initialization isn't actually necessary. You could have any value here and it wouldn't matter because it's always going to get overwritten by the first line. But then what we do is we loop through our instructions. If it's a mask, then we overwrite our mask. And otherwise, we go into this whole routine right here, which I've broken down into 3 sections. So what we do here is we still copy a list of the mask, and then we do the rest of our initializations here. So you'll see we're doing what we did to vals to index this time, because we need to modify index instead of val. So we're doing the same thing where we're converting it to a binary string representation of the number and adding a bunch of leading zeros to make it the same length as cur. And this time value is just going to be whatever actual number is passed on that side of value. So then I'm also initializing an empty list called floating that's going to hold all the indices of all of our floating numbers. So then what I'm doing here is I am looping through cur. If cur at that location is a 0, then I overwrite cur at that location with ind at that location. So we just accept whatever it is because that's what we do on zeros. If it's an x, then I add that index to floating. And if it's a 1, then we leave it untouched because it is supposed to stay a 1. So the reason why it seems like what I'm doing is backwards from what it said in the instructions is because instead of modifying the memory address, I'm modifying the mask because I just found that to be a little bit more convenient. But yeah, you could do it the other way too. So then what I'm doing here is you'll see I have another loop here, and this is where I am actually doing all of our modifications to our floating number values. So I'm looping through 2 to the power of length of floating. So if you'll remember, floating has all of our indices of where our floating numbers are. So if you think about that, right? So if we look at this, for instance, so we have an x here, an x here, an x here, an x here, and 3 x's here. So that's 7 x's, right? So we need to replace all of those with zeros and ones such that we get every single possible combination. Well, how can we do that? Is we can actually say, okay, let's ignore everything else in this mask, and let's say we had a binary number that was just all of these x values glued together in the order that they are. Well, the way that we could get every single binary number of that form is just to loop through the actual integers up until 2 to the power of whatever that is. So this is going to end up being 2 to the power of 7, which is 2, 4, 8, 16, 32, 64, 128. So if we do that, if we had 1s in all of those spots, that would be the same as having 127. So if we just loop through the range of 128, we're going to get every single possible number that a binary representation of that is. And we can go ahead and just turn that into a binary number, replace all of those numbers, and we're good. So then what we do there is I go ahead and just copy cur into cur ind, because if you'll remember, cur is our base thing of our initial pass of the mask. So that's going to be like replacing all of the zeros. So then I need another copy of that because we're going to get multiple indices from this. So then I have bin stir here. So what this is if you'll remember, I, which we're looping through right here, is going to give us an integer. So what I'm doing there is I'm converting that to a binary string, and that is going to give us our sort of mask that we're going to pass on and replace all of the x's with. So then you'll see here what I'm doing is I'm just adding a bunch of zeros to the start of it to make sure it's the same length as floating. Because if you think about it like this, when bin stir is 1 and the full-on length of floating thing that we need there is going to be like 7 long, like we had in our example, I'm just going to have that 1, but I want it to be 0, 0, 0, 0, 0, 0, 1. So I'm adding on my leading zeros to make that match so that we can loop through things nicely here. So then what I am doing here is I am looping through both floating and bin stir at the same time. I could do it like I did before by just looping through one index. That would work as well. But I just did it like this for some reason. There's I have no real reasoning why. So what we're doing here is we are assigning the current index sub I, which I is going to hold whatever floating value we're up to, and I'm assigning that to j. So j is going to be whatever is in our bin string at that current point. So let's say floating here. So if we had it in our example that we were using before in this one, where we have those 7 x's, right? So if we get up to where binster is the binary representation of 127, which is just going to be ones in all those places, we're going to place this one with the 1, then we're going to place that one with the 1, then that one, then that one, then that one, then that one, then that one. If it's 126, we're going to replace all of these with 1s, except for the last one is going to get replaced with a 0, and so on and so forth through all of the possible different combinations of that. So at that point, cur_int is going to hold an entire binary number once we finish up with this loop. And that binary number, if we convert it back to an integer, is, or whatever, that is going to be our actual memory address. So here, since I just need them to be unique and I don't actually need them to use the same numbers as I did in part 1, I just join this into a string. There's no reason to convert it back into an integer. And I just say that our values sub that binary string right there is going to be equal to our val. And then once we do that for every single instruction in the list, remember this is all inside this outer inst in instructions loop, then we can just go ahead and return the sum of the values in our vals dictionary, and that is it for part 2. So I hope you enjoyed today's video. If you did, be sure to leave it a like, get subscribed to me, and turn on post notifications so you don't miss any of the future episodes. So today was just more sort of rule following. Instead of any super interesting algorithms, but it was still a pretty fun one. So I hope that things will continue improving, and I will see you in the next one. Goodbye.